All right, so without too much further ado, I think I give the floor to Alessio, who will tell us about the regularity of optimal transport.
So thank you very much, Jan, for the introduction. I would like also to thank the Schrödinger Institute for allowing us to organize this program and to have these workshops. And so it's very nice, and I'm very happy that we're all here. I see many friends in the audience. We have been discussing with Jan that, of course, is not usual for organizers sometimes to speak, but I could try to do something between the school of last week and the workshop of this week. And something that, I don't know, is not very often taught in these kind of events, because it's always tricky to discuss about optical regularity, because usually it requires a lot of background. I thought that in a couple of hours at least I could give a sense of what has happened in the last years in the regularity of optical transport. Sometimes I would like also to make sure that everyone starts on the same pace. So I will actually start very basic. So the first probably 15 minutes will be kind of boring for most of the audience, but at least I'm sure that I don't lose anyone. So the first part will be really about starting to build optimal transport maps. What's the theory? How you get the formula for optimal transports, because it's very important. So the reason why you have regularity of optimal transport map is because they have a structure. So everyone knows, or essentially everyone knows, the Brenier theorem. So we have Jan here, and Brenier theorem tells us that when you do the optimal transport problem for quadratic cost, the optimal map exists, is unique, and is the gradient of a convex function. And it's the fact that the optimal map is the gradient of a convex function which is behind the fact that we can prove some regularity results for optimal maps. Now, if I change the cost, I don't get any more gradient of a convex function. Things get more complicated, but still is in the cost, is in the, let's say, the structure of the optimal map, which is going to be related to the cost, that it's hidden some, let's say, structural properties that are going to be key for regularity. So that's why I wanted to go back a second to how you prove existence of optimal maps and why you get that kind of structural properties. So let me start from the very beginning. So we have optimal transport. So the most classical setting, I have two measures, mu and nu, each defined in two sets, x and y. For most, essentially all my lecture, this will be x and y are going to be subset of a Rn. A bit in the end, I will mention also the case when they are maybe subset of a Riemannian manifold. You can do even more general situations, but for my purpose, that's all I need. So what do you do in optimal transport? You look for a map T such that, so look for T such that T push forward mu equal nu. So I will use maybe some colored chalk. So that's the usual thing. You want, I prefer to set the notation because you will see the difference later with the Alexandrov solutions. So T push forward mu equal nu means that whenever I take a set A and I look at the counter image, the mass that mu gives to the counter image is equal to the mass that nu gives to the set. Okay, so nu of A equal mu of T minus 1A for every A. And you ask the following. You ask that, so you are given a cost function, C of x from x cross y into R is our cost function. So C of xy is the cost to send a point from x to y. And so you want to minimize. So when T minimizes, the total cost. So the total cost is the integral over x of the cost of sending one point from x to t of x, and then you integrate with respect to the total mass. So among all transport maps, C is the one which minimizes this transportation cost. So as you know, this is a very non-trivial problem in the calculus of variation, and essentially is non-trivial for two reasons. So so if you consider minimize integral C of x, S of x d mu among all maps that transport mu onto nu, this has two issues. So the first issue is that the set of maps such that S push forward mu equal nu may be empty. And then the second issue is that the constraint S push forward mu equal nu is a nonlinear constraint. So it's very difficult, also a technical problem, to kind of proving existence. So there are technical issues if you try to minimize this problem. And that's the reason why you change the problem. So this is what Kantorovich did. We are in the 40s, 1940s. So Kantorovich just made the following observation, that rather than looking for maps, we think of maps as graphs. So let's say that I have a graph S. So this is the graph of S in the product. So this is X and this is Y. Then I have pi 2 and pi 1, the canonical projection from on the first coordinate on the second coordinate. And then the observation is that if we set gamma of S to be identity cross S push forward mu, so we take the mass of mu and we put it on the graph, then you have the following properties. So first thing, you can look, okay, maybe I change Blackboard. Then the first thing, you can look at the marginal of this. So if you compute P1 push forward of gamma S, this is P1 composed with identity cross S push forward of mu, because the push forward is functorial, so you just compose. And then pi 1 compose identity cross S, it's just identity. So this is identity, this composition, and so you get mu back. And vice versa, if you do pi 2 push forward of gamma S, here you get pi 2 composition identity cross S push forward of mu. And now the second component here, pi 2 composed with this, with identity, is nothing but S. And so this is S push forward mu, which by assumption was equal to nu. So in this way, the transport constraint, S push forward mu equal nu, becomes that the first marginal is mu and the second marginal is nu. And also, what happens is the following. So the integral, so now I will use the change of variable formula for the push forward. The integral of C of x, S of x, d mu of x. This is the integral of C compose identity cross S d mu. I can look in this way. And by the push forward formula, this is the integral of x cross y of C push forward here, so d gamma of S. So what have I used here? I mean, this is a standard fact, but maybe let me make a remark. So in general, so let's say, given a map, if I know that, well, let me do it with T. Well, no, T is 2. If I have a map, F, capital F, okay? If I know that F push forward, let's say mu equal nu, what does it mean? This means that for every A, nu of A is equal to mu of F minus 1 of A. This is equivalent. So this is for every mu nu F. So we have this. This is equivalent to what? This is equivalent to say that the indicator function of A integrated in the nu, so that's the left, is equal to the integral of the indicator of the counter image, indicator of F minus 1 of A in the mu. But the indicator of F minus 1 of a set A is the same as the indicator of A composed with F. So we have, this is the same as the indicator of F of A composed with F, d mu. Oops, sorry. So what happens is that the push forward is telling us that this identity is true for every A. And so if it's true for every A, this is true for every sum of indicator functions. So for every sum I from 1 to n of lambda I indicator functions of AI d nu. This is a linear constraint, so you can start to take sums of indicator functions or convex or combinations of indicator functions. And then you have that this is equal to the sum over I of lambda I indicator functions composed with F d mu. And again, by approximation, this is then true for every test function. So integral of any test function psi d nu is equal to the integral of psi composed with F d mu. So this is how you go from this formulation of the push forward to this formulation of the push forward. So this corresponds to the case where you test this with indicator functions. It's the first line. And so you see, by this formula, you can apply it in this case. The map F will be identity cross S, and then you have this identity. So this was just a standard equivalent formulation of the push forward, which, again, is going to be useful later. So, okay, so what is the Kantorovich formulation then? So Kantorovich, as I say, the Kantorovich observation is that you have three quantities. So you have the push forward condition on S has become a marginal condition on gamma. And then the cost of S actually can be translated immediately as a cost condition on gamma. So then Kantorovich problem, is simply to minimize the integral of C of x over y d gamma xy over the product over all gamma such that the first marginal is mu and the second marginal is nu. And notice that this, or let's say this is an inf. And what this computation I did proves is that this infimum is smaller than the inf over S push forward mu equal nu of the integral of C of x of S d mu of x. Just because every element here induces an element here. So you are minimizing over a larger set. So this is the new formulation. And in the Kantorovich setting, it's very easy to prove existence of minimizers. Essentially, is just minimizing a linear functional over a linear constraints. So the theorem, this is not complicated, is that, let's say, if the cost C is continuous, there exists gamma bar minimizer. A priori may not be unique. So now, once you have the minimizer, what do? There are several ways of obtaining what is called the Kantorovich duality. One that I like is the following. So once you have the minimizer, you say, OK, I have my minimizer, which will be a measure in the product. So this is x and this is y. And it will live somewhere here. Let's say this set is the support of the minimizer, gamma bar. Now, geometrically, what does it mean, this set? So geometrically, saying that a point is in the support, let's say a point here is in the support, is a way to say that there is some mass here in x1, which is sent onto y1. So whenever x1, y1 is in the support, it's like saying, OK, a bit of the mass is sent by gamma bar from here to here. Now, suppose that I take n points here in the support. So this is xi, yi. And then what I'm saying is that, OK, I have n points, and each of these points, each xi is sent onto yi. But now, gamma is optimal. So the fact that gamma is optimal, it means that not only, so let's put it in this way. So xi, yi is in the support of gamma. Gamma bar implies that some mass, informally, goes from xi to yi. I mean, this doesn't mean too much because maybe every point has measured 0. So you really need, it's like to say there is a little mass around xi that goes to some mass around yi. But let's be a bit informal. So some mass goes from xi to yi. Now, here I have, let's say, n points at my disposal, x1, xn. Here I have n points at my disposal in the target, y1, yn. And gamma bar is optimal. So the fact that it's optimal, it means that a priori, I could start to permute the points and say, OK, instead of sending mass from xi from x1 to y1, let me send mass from x1 to y2. And then from x2, the mass that then was going from, so here, let's say this is 2. So I say, OK, this point, instead of sending it here, let me send the mass here to this point. But now, OK, the mass is coming from here. So y2 already got mass. But if y2 already got mass, the mass that was coming from here, I cannot send it here because the mass now already is coming from the first point. So the mass here, let me send it rather here now. And then this point is already taken from this one. So then the mass that was going from here, instead of sending here, let me send it to the only point left, which is this one. So I'm permuting. So I'm just changing from each point I'm choosing a different source. And the fact that gamma bar is optimal should tell me that this new choice should not be good. I'm using more cost, because otherwise gamma bar would not have been done in that way. So by optimality, the fact that if I know that xi, yi is I from 1 to n is contained in the support of gamma bar, then if I look at the sum of the costs to send xi to yi, this should be less or equal than the sum of the cost if I start to send a mass in the other point. So the cost of sending xi to yi plus 1. So I just permute the targets. with the convention that ym plus 1 is equal to y1. So I have to close up. So this is property C. So this has a definition. So this has a definition which says that the support of gamma bar is cyclically monotone. Okay? So the implication is you minimize Kantorovich, you get a measure, and by minimality, you prove that the support is c-cyclically monotone. And now here it comes a theorem. Which says the following. Let gamma be a subset of x rho y, be a c-cyclically monotone set. Okay, so what does it mean? It means that whenever you take points xi, yi in gamma, in capital gamma, that inequality holds. So the cost increases under permutations. Then there exist functions phi from x to r, psi from y to r, such that phi of x is equal to the sup over little y in y of minus cxy minus psi of y. And phi of x plus psi of y plus c of xy equals 0 on, let's say, for all points x and y in gamma. Okay. So, so let me maybe put a star here. Yeah. Let me put a star next to this. So now we can start to play a bit. So you see the chain of implications. We start, I say a minimizer is cyclically monotone, and then I say that a cyclically monotone set has some structure. There are some functions that do that. And notice that so then I will combine these two facts. So I will apply this theorem to the support of gamma bar. Okay, so let's make first some comments about this. So some remarks. So first, if star holds, we say that the function phi is C-convex. So it's a kind of convex function. And let me explain, we'll explain this in 2 seconds. Second, notice that star by star implies, so what does it imply? This implies that phi of x is a sup. So phi of x is always greater or equal than what is inside here. So star implies that phi of x is everywhere greater or equal than minus cxy minus psi of y. Just because I removed the sup for every x and y. Then 3. If I take c of xy equal minus x dot y, so the standard scalar product in Rn, then what happens? Then phi of x is equal to the sup over y of x dot y minus psi of y. And you may notice that, what does it mean? For every y fixed, this is just an affine function, something like this. This is the function x dot y minus psi of y. And now if you let y vary, I will have a soup of affine functions. And when I take the soup of them, I get phi, and phi is convex, being soup. So phi convex. So when the cost is minus x dot y, C convexity is equivalent to convexity. Okay, so yeah, the last thing, it's a regularity property that I need on phi. So phi is the soup of costs. So if we assume that the cost function C dot y, so for every fixed y, the cost function as a function of x is Lipschitz. At least, let's say, locally is Lipschitz. In x. Uniformly with respect to y. So it means that the Lipschitz constant is bounded independently of y. Then, what do you have? You have, by the formula on phi, star, your phi is a soup of Lipschitz functions, because for each y fixed, this is a Lipschitz function. Uniformly Lipschitz. And now if you take a soup of uniformly Lipschitz function, you get a Lipschitz function with the same. So then phi by star, phi is Lipschitz inside x. Okay, so for free you get a regularity property on phi. Okay? So in particular, this implies that phi is differentiable Lebesgue almost everywhere. Okay, now, so these are the properties. So now we go back to Kantorovich. So we have back to Kantorovich. So what do you do? First, you find gamma bar optimal. Then you say that gamma equal the support of gamma bar is c-cyclically monotone. It's what we saw there. Then you apply this theorem that tells you that if you have a c-cyclically monotone set, there exists phi and psi that satisfy that properties. So then you find phi and psi as in the theorem. And now I'm going to assume that C dot y is uniformly Lipschitz and of class C1. Actually, so I can take derivatives of the cost. So this implies, in particular, by what we saw, that phi is differentiable almost everywhere. Because if the cost is Lipschitz, phi is Lipschitz, so phi is differentiable almost everywhere. So we are here. Very well. Now what you say? You are here, and then you say, I have these properties. And now I say, take x bar, y bar, a point in gamma, so the support of gamma bar. with x bar such that phi is differentiable at x bar. So I take a differentiability point for phi. Since I have a differentiability point, I can go back to the two properties. One is that phi on gamma, phi plus psi plus c is 0. And second, elsewhere, I have an inequality. So we know since x bar, y bar is in gamma, that if I take the function phi of x plus psi of x bar, of y bar, plus c of x y bar, so I keep x free and I fix y bar, then this function is non-negative, is the property 2 that I wrote there. And it's equal to 0 at x bar. And that's this property. Whenever I'm on gamma, I have equality. So I have a function of x, which is greater or equal than 0, vanishes at x bar, and remember, phi is differentiable by assumption, and c is c1, so it's also differentiable. So this implies I can differentiate. So, and I get that the gradient with respect to x at x bar plus the gradient of the cost is equal to 0. So this is the information I get whenever x bar, y bar is in gamma, and x bar is a differentiability point for phi. Okay, so here I used the only two information I need is these 2 points are in gamma and phi differentiable. Okay, now if you reach this point, so this will be the structural condition, we'll see in a second, that will be crucial for our transport map. But let's say you reach this point, and now once you reach this point, you would like to say that y bar is uniquely characterized by x bar through this relation. So you would like to say that there exists a unique y bar which can satisfy this relation. Because remember, x bar, y bar being gamma means that your plan is sending x to y. But then you want to, sorry, x bar to y bar. But then you would like to say, in the ideal world, is that, so this is Kantorovich problem, but we started from the optimal transport problem where you wanted a map. So you would like to say that x bar is sent to one point, y bar. So you would like to prove that this point is unique. So there exists a unique target for x bar. And that's why you would like to use this relation to characterize y bar. So now you need to make an assumption. So hypothesis. This is called twist assumption. That tells us that the map that to y associates, so for every x, if I look at this the map as a function of y now, grad xc of x dot, this map is a homeomorphism. Let's say, let me make a regular. In particular, it's injective and invertible. It's an homeomorphism on its image, I'm going to assume. In particular, there exists an inverse. Let me call the inverse capital Y of x dot of this map. So x here is a parameter, and I'm looking this as a map. So c is a function from, so c of x dot, so c is a function on, let's say, Rn cross Rn. The gradient, now it's a vector. So this is a map from right? So grad xc is a map from x cross x, x cross y into Rn. And these are subset of Rn. So in particular, if you look at grad xc for x fixed, this is a map from y to Rn into Rn. And then what I'm asking is that there is an inverse of this map that I denote by y. So this is an assumption. But now, if you combine this hypothesis with this relation, what do you get? Is that, yeah, in fact, okay, let me do one thing. Let me put a minus here, sorry. It's going to be nicer, the formula. Minus grad is, is the same. You just change the sign. So you see here, the relation is grad phi of x equal minus grad x of c x bar y bar at every point. And now you can, at x bar fixed, you can invert this relation. And then this is equivalent to say that y bar, so you can invert this map. So y bar is equal to capital Y of x bar grad phi at x bar. So under these assumptions, you see, the crucial thing I have assumed here is the twist condition. And in this way, you have a formula that tells you that y bar is uniquely identified by x bar and this gradient. Okay, so we are here. Yeah, so what did we say here in sense? So for x, for every x differentiability point, of phi, we can define the following map: T of x to be y of x grad phi at x. So we have this defines a map at every point. And now what did we prove? So what I have just done proves is the following. So here I have mu, here I have nu, and somewhere I have my, let's say, gamma. And now I say, okay, take a point x here, which is a differentiability point. And then ask yourself, how many points there are here? So in the support of gamma bar, sorry, in the support of gamma bar above x. So all the points here are the points which gamma bar send from x somewhere. And what this proves, this formula, is that it tells you, okay, take any point. Maybe here I put x bar, just one. Take any point here, x bar, y bar. Then in fact, y bar is unique because it's uniquely identified by x bar and grad phi. So here, this formula tells me that y bar is equal to T of x bar. So for every x differentiability point, there exists a unique point y such that y belongs to x such that x, y belongs to the support of gamma bar. Which implies that on every differentiability point of my map, of my phi, I can only have a graph. So above this point, every time I have differentiability, Here, in fact, I don't have a full set. I just have one single point. So for every differentiability point, I have only one single point above. So above differentiability point, gamma bar is a graph. Of course, this is not enough to conclude, because maybe gamma bar could be, maybe there is a point here which is not differentiability, above which gamma bar is not a graph, and maybe there is some mass here. Maybe mu gives some mass to points which are not differentiability points. So we have this property, and now you make a second assumption. Mu is absolutely continuous with respect to the Lebesgue measure. In this way, mu almost every point is a differentiability point for phi. So it means that mu almost everywhere. So even if there are non-differentiability points, these are measured zero for mu. Mu will not see them. And so it's like if all points were differentiability points. And so it means above every point there is only one. And so in fact, gamma bar is not something sparse. Gamma bar will be just a graph now, because above every point there is only one point. So the corollary is the standard, let's say, theorem in optical transport, that if you take x and y are subset of Rn, and then assume that C is a C1 cost, C satisfies the twist condition, and mu is absolutely continuous with respect to the Lebesgue measure, then there exists an optimal transport map. And T is characterized, T of x is equal to y of x grad phi at x almost everywhere. Which is equivalent to say, if you recall the definition of y was the inverse of minus grad c. So the other way to write it is that grad phi of x plus grad x c of x t of x is equal to 0. It's the same thing. Okay, to be honest, so the map is actually also unique. Now I don't want to spend more time than needed on all this. But let's say this is at least proves the existence of optimal transports. And what is crucial is this formula. So in the particular case, now, in the particular case that I'm going to consider the quadratic cost. So now, if we look now at the quadratic cost, so the quadratic cost is what? Is c of xy equal x minus y squared over 2. Okay, I don't like this cost, so I'm going to do another thing. So the optimal transport problem from this cost is the minimum over s push forward mu equal nu of the integral of x minus s of x squared over 2 d mu of x. But this is equal to what? The minimum s push forward mu equal nu of the integral, and then I can develop the square. So this is x squared plus s of x squared over 2 minus x dot s of x d mu. And now this here, I keep going, this is equal to the integral of x squared over 2 d mu, the first step, the first term. Then I have the integral of s of x squared over 2 d mu. But by the push forward condition, the integral of s of x squared over 2 d mu of x is equal to the integral over y squared d nu of y. I push forward, y squared over 2. And then I have plus some, so you see these first two terms do not depend on s, because it's just second moment of mu plus second moment of nu, plus the mean over s push forward mu equal nu of the integral of minus x dot s of x d mu of x. And so you see that instead of minimizing the quadratic cost, I can minimize c of xy equal minus x dot y. That's the one I discussed at some moment before when I told you that c-convex functions are convex for this cost. So I like this cost better. And now with this definition, what happens? So the relation for the transport map, so in this case, phi c-convex, we have already seen it means that phi is convex. So c-convexity in this particular case is just the standard convexity. And then the transport condition is that grad phi of x plus grad xc of x t of x equals 0. But what is grad xc? Grad xc of xy is the derivative with respect to x of this is minus y. So this is minus t of x. And so the final relation is that t of x is the gradient of phi, phi convex, which is Jan's theorem. Essentially, we just proved the Jan's theorem. One more thing before we take maybe a break. So we have now a map which is either the gradient of a convex function in the quadratic case, or is some transformation through this map y of a gradient of a c-convex function. And now you want to find a PD in order to understand the regularity of optimal transport. So, how does it go? So I want to use the push forward condition. Okay. So Jacobian equation. So we are going to assume from now on that mu as a density, let's say f dx, and nu as a density g dy. Then since t push forward mu is equal to nu, this means that for every test function, for every, let's say, key test function, the integral of k of y, g of y dy is equal to the integral of key composition with the transport map, so k of t of x, f of x dx. So this is just the push forward condition. But now, formally, what you could do here is to say, okay, let me do a change of variable. Let me set y equal t of x. And then dy will be the modulus of the determinant of grad t dx, at least formally, change of variables. And then this left-hand side becomes the integral of the characteristic of t of x, g of t of x, determinant of grad t dx. And now you compare this expression with this expression, and you say these two expressions have to be equal for every chi, for every test function k. Therefore, f of x must be equal to g of t of x times the determinant. So from here, we get that the determinant of grad t is equal to f of x over g of t of x. So this is the Jacobian. And now, for the quadratic cost, we say that t is the gradient of phi, where phi is convex. So you can insert t equal grad phi here, and you get the determinant of the echelon of phi equal f of x divided by g of grad phi at x. And this PD is called Monge-Ampère. So this is why optimal transport is linked to the Monge-Ampère equation. So I think I can stop here, and then in the next hour, we really start to just discuss regularity theory for this PD. Thank you.
Thanks a lot for a beautiful lecture. Are there any questions or comments on this one?
Just one little one. So, on the quiz condition you have for the cost, is there any general class of cost function you can check to satisfy the condition? It just left as, let's say, something you need to check time by time. Like
Yeah, essentially you need to check it time by time. It works. So twist. The standard ones are, for instance, all strictly convex functions h of x. If you take h of x minus y, where h is convex, this works, uniformly convex. So, for instance, x minus y to the power p greater than 1, it's okay. Or if you are on a Riemannian manifold, the distance to the p on Riemannian manifolds. So at least these are very standard and nice cases where this kind of twist condition works. Then if you are also cost-induced by Lagrangians in general will satisfy this, but yeah, you need to check it at some moment. So if you start to make it more complicated, you need to check it.
the continuity of the inverse is somehow crucial.
No, okay. For the existence of a transport map, in fact, you don't need any continuity. You just need to invert that map. It doesn't matter. As long as it is measurable, that's okay. Also, the assumption C1 on the cost is not so necessary for many things. Let's say I was more just, for me, it's anyhow, at some moment, I would need to take derivatives of the map Y. So for me, the map has to be actually at least, not only it has to be an homeomorphism, it has to be a diffeomorphism, because otherwise I cannot take derivatives of Y. So from my perspective, I'm assuming that the cost is as nice as I want, let's say. It's not there the issue. But of course, many things can be weakened.
Any other question at this point? If not, then we resume the discussion at the coffee break.